Okay, welcome back to the second half of the class. And what we're going to do now is talk about the Gaussian map. And here, this is an interesting case because, well, on the one hand, everything is Gaussian, but on the other hand, we're going to see that the achievability region is in fact exactly equal to the polytope. So it's a polyhedral achievability region. So in the Gaussian channel, and we're also going to talk about a number of interesting decoding possibilities and how the different decoding possibilities gives us different subsets of the achievable region. So what is the Gaussian map? So the Gaussian map is fairly simple. Basically, we have y, which is what is received. We have two senders, x1 and x2, each of which is subject to some gain, g1 and g2. And z is noise. And so gi is channel gain, and the noise is presumed to be zero mean Gaussian noise with variance n over 2. Okay. And so the transition, basically at transition time I, what happens is the following. We draw a random number from here, draw a random number from here, take this combination where z is this noise term, the noise is independent of everything else, and we get a resulting y back. And that's the ith channel use. Okay. And again, just like in the Gaussian channel case, in order to make this sensible, we need power constraints. So we have a code book and a set of code words, and for the ith channel, we have this power constraint. So by taking, for example, the sum of the n channel uses of the kth, I guess it's we have inputs 1 and 2 for k is equal to 1 and 2, and then we take yeah, that's right. So for message wk, we're taking the ith symbol for the kth sender, and then that has to be less than or equal to n times the power. So 1 over n times that sum has to be less than or equal to the power constraint. And we have this many messages for each sender. So we have 2 to the n rk for sender k. And again, k in this particular case is just either 1 or 2. Okay, so this is theorem. This is the theorem that is whose reference is being missing, but this is basically the theorem for the generic map. And we're going to extend this to the Gaussian map channel. And we're going to utilize the Gaussian capacity function. So, so remember that this capacity function had the following form from the Gaussian channel. It was 1/2 log of 1 plus the signal noise ratio, and the signal noise ratio is expressed as P1 over N. Okay, and that basically says, okay, when we have x, this is conditional on x2, the throughput between x1 and y is equal to this. Okay, so condition on x2, what does that mean? This is an important thing to understand. Why does this work? When we condition on x2, it's saying that we know x2. Okay, so x2 essentially becomes known, and it doesn't affect the channel at all anymore. The only thing that we have that disturbs the source, the sender, in this particular case is x1, is the noise, which is power n. Okay, and so therefore we get the standard Gaussian channel case. And similarly, we have a similar bound for this guy, and a similar bound for this guy as well. Right? Except that in this particular case, we have the sum power on the numerator. Okay, so let's say that we have signal to noise ratio value f, and let's just define this function c. This is the Gaussian capacity function. It's 1/2 of log of 1 plus s. Okay, so then we get the following rate bounds. So rate 1 is less than or equal to the capacity with this signal to noise ratio, P1 over N, and which we're just going to say that's equal to C of S1, plus S1 is going to be equal to, it's equal to C, S1 is equal to P1 over N. And similarly, we have this bound for R2, right? And then we have this third bound for the sum. Right. Now, and this is equal to C of S1 plus S2. Okay, remember S2 is equal to P2 over N. Same denominator, so they combine. The S's combine additively. Okay. So basically, what's happening in the sum rate case is that we're encoding these things together based on the best product distribution, and that's the best we can possibly do. Okay, it's the sums of these powers. And so what we end up getting is the following region. Now, there's some interesting points on this region which I want to point out to you. So first of all, there's this point here. Let's see if I can zoom in a little bit. This point here that I just highlighted in black corresponds to sender 1 basically turning off. And we get C of S2, which is basically the signal noise ratio, because remember, we've got just the power of sender 2 over the noise, which is C of S2, which is this bit here. So that's where sender 1 is off. Similarly, we can get this point here, okay, where sender 2 is turned off and sender 1 is on. And we basically are conditioning on sender 2, and so therefore we get C of S1. This point here is kind of interesting. Let me just write this out in another way. We're going to see this in a few other slides. This is C of S1. Writing is not working. S1 over 1 plus S2. All right, so that is basically, that point is sort of not conditioning. It's basically the numerator here is the signal to noise ratio of 1. The denominator is basically what happens is if we treat S2 strictly as noise. And you'll see why this point actually makes sense. The way this works is the following. First of all, if you look at these equations here, without loss of generality, we can just sort of set n is equal to 1. Okay? So everything is just, when n is equal to 1, we've got this guy. We've got that S1 is equal to P1 and S2 is equal to P2. So then in that case, this right-hand side becomes C over P1 over 1 plus P2. So the power of the second sender, or the second sender, is just noise, and it's additive noise in addition to Z from the perspective of S1. So that's not really conditioning on S2. Instead, that's just treating it as noise. And so now our noise threshold is higher, right? Because we have the additive noise, S. We've got P2, which is treated as noise, and we've just got a new signal to noise ratio, and so we have this capacity. So what is the difference between this point here and this point here? The one on the right is basically when we condition on S2. It's saying that we know what S2 is. And again, because it's this V structure, it's that Y is equal to X1 plus X2. It's the case that the right-hand side case, that's the conditional mutual information. That's the mutual information between Y and X1 given X2. That's this one right here. The left one, this one right here, is just the mutual information between X1 and Y. And that's not conditioning on X2. That's basically saying X2 is effectively just noise. And so we have to deal with it as noise. And in the Gaussian channel case, it's basically adding it to the noise variable. So the noise variable becomes S2 plus Z. And then symmetrically, we have this stuff over here on the vertical axis as well. So does everybody understand this figure? Or why we get these points? Now, the other thing is that we get these other points for the same reason. We can never communicate, the sender 2 can never communicate greater than this line. But if we are communicating at this point here, then we know, or at least what we're going to see, is that we can, depending on which coding strategy we use, still send something for S1. We don't have to sort of completely turn off S1's rate. We can still do something and get this point here. Similarly, if we're communicating at sort of this limit, at R1's limit, S2 can still send something. But it can't send anything that ever makes the sum rate bigger than this constraint there. Because that's the best possible. That's when we optimize over Px1, Px2 of that mutual information quantity.
So, if you want to get the points, the pair of rate on the line. So what would be the strategy?
To get a point here?
Yes, without like time sharing.
Well, we're going to talk about that. I mean, time sharing is one very simple way, and that shows that in some sense it's achievable, right? So we're going to talk about a couple of coding strategies to get points on the line, including some interesting ones. But one strategy would be to use this sort of typical set decoding strategy where we have some additional variable q, and we decode both q and mixing variable and the x's together.
So this q thing I'm trying to understand is, does it mean that, let's say in the binary case, so you have two cases, does that mean that let's say 0 gives you a pair of code words and the other one another pair of code words, and that's just two possibilities?
So that's right. So what we're decoding is q, x1 and x2, and the typical guy is going to be, some half, depending on what the probability of q is, we're going to get code words such that it gives us the rate anywhere on that line. But we have to decode all three together: q, x1, and x2. It's trickier. I mean, it's typical set decoding. And you can show that the rate, the probability of error goes to 0 and goes to infinity. It's not exactly a particularly nice way of coding, but it exists. It's feasible, at least theoretically feasible. Okay, so let's treat. This is I guess I've already sort of mentioned these cases, but let's go through them in a little bit more detail. So there's three cases. There's a bunch of cases we're going to talk about. So one case is where we treat the other code as noise. So AN stands for as noise. And when we treat the other one as noise, what we said is that what we get this set of rate constraints. Okay. So that becomes an inner bound on the region. So I have the figure here, which I should have actually probably put a little bit earlier. So let me give you these figures. So here's the power type on the left and on the right. On the left, we have a high signal-to-noise ratio case, and on the right we have a low signal-to-noise ratio case. So the as-noise instance, the as-noise polytope corresponds to these guys here. This is saying you can do anybody here, which is in the high signal-to-noise ratio case, and anybody here in the low signal-to-noise ratio case. Okay. Now, one thing that's interesting is that when you're in the low SNR rate, that the as-noise region is such that the upper right-hand side point of that yellow region is greater than this TDMA thing. Now, the question is, what is the TDMA case? So the next thing we want to do is see how we can actually achieve. I think that's the next thing.
So you can imagine the low SNR case is like larger?
Yes, the as-noise case is larger. So we want to next do this region here. And similarly, this region here.
So the rectangles are the as-noise regions, the other green ones?
The green ones are going to be the time sharing between the two extremes. So the time sharing between the two extremes are saying, so remember we talked about this point here? Remember the only thing that difference is here's high SNR and here's low SNR. So these are two of the same things, just for different signal-to-noise ratio cases. So this point that I marked in red, these points that I marked in red, correspond to achievable points by basically conditioning, right? So there we turn off the rate of R1. Okay, so like in that particular case, as soon as we turn off R1, or meaning set R1 to equal to 0, and basically the sender 1 doesn't communicate. Sender 1 always sends 3, or something, right? Or whatever it sends some constant thing. We always know what that is. And then on the right-hand side, we just always subtract it out. It becomes a constant. We subtract it out. We could send 0, in which case we don't even have to subtract it out. And we just do coding between sender 2 and y. When we do that, then we get this bit here. We saw this is just C of S2, where that's the signal power, that the rate at which we can communicate, capacity, the limit on the rate at which we communicate is dependent on the power of S2, power of X2, the sender 2. And then we know we can get this line in between by doing TDMA. Now what's interesting about this plot is that when we're in the low SNR case, the very simple strategy where we're doing simultaneous coding by treating the other one as noise is such that we get a weight pair which is better than the time sharing guy in between. Like so this, let's do the low SNR, move in for a bit. So we get a better, but the time sharing is actually worse for this region.
And when you say low SNR, you mean that the power of each of the transmitted signals is
Lower.
Low compared to the power of Z.
That's right, which is assumed to be 1.
Right.
So low SNR means low power. But that maybe kind of makes sense because when everybody is doing low transmission power, maybe they don't disturb each other that much, and it's better to do simultaneous coding than it is to do time sharing. Because it's kind of like saying, well, look, you're not very loud anyway. Like, let's say the two people are talking to you or something, and we're not saying very much. Like I'm not saying a lot of stuff, and some other person who's talking is not. What we could do is we could swap. Like I could talk for a minute, and then this person could talk for a minute, and I could talk for a minute. But if the amount of information we're sending is not very high, because our power is not very high, rather than doing time sharing, we might as well both talk together, and you can sort of, you can listen to both of us, because we're not saying a lot. And that's better than time sharing. And that's what this region is here. So that's this figure here. This case B. TDMA. So TDMA is just a very simple strategy where we're just taking this combination of rates. Okay? And that's what gives us that line. Okay? And alpha is basically the fraction of time that we spend on one sender versus the other sender. This next one is an interesting one. This is TDMA with power control. So the idea is that if we do TDMA, we can still achieve the overall power constraint if we boost the power of the sender that's currently sending by something that's inversely proportional to its fraction of time. Right? Because when you think of alpha times x divided by alpha plus 1 minus alpha times x1 divided by alpha plus 1 minus alpha times x2 divided by 1 minus alpha is still going to satisfy the power constraint. Let me write that down. Where should I write it down? It's like, if we do, basically, if you think alpha times x1 alpha plus 1 minus alpha x2 over 1 minus alpha, that's still going to be less than or equal to power, as long as x1 plus x2 is less than or equal to power. So that means, like, because the amount of time we're spending, thinking about, like, we've got these n channel uses. The first alpha fraction of the n channel uses are going to be, so it's alpha times n. But then when we sum up the powers of those guys, that's just going to be divide each one by alpha. So each one is sending at a greater power, and we still satisfy the power constraint. So that's basically what's happening here. So for sender 1, the block length n is blocked into a partition. The first is of length alpha n. The second is of length 1 minus alpha times n. So that's just time. That's the time division. But then for that first block of length alpha n, we send at power p over alpha. And the sender with 2 weights. It doesn't do anything. And then for the second block, we send at power p over 1 minus alpha. So whoever gets a shorter time length gets to send at a bigger power. And you still achieve the overall power constraint. And so what we end up getting is a rate region which corresponds to this. Now, the question is this useful? So we're still getting sort of this mixture between these extremes, but it's not really a clear mixture anymore, because as we vary alpha from 0 to 1, C which is a nonlinear function. In fact, it's this. What kind of function is it? It's log of 1 plus that thing, so it's a concave function, right? So it's going to get bigger, and it's going to have this point at which c gets bigger, right, before it gets smaller, if anything. And so what we're going to get what we're going to get in this TDMA with power constraints is something that looks like this. So here's C again. Let me just draw these with a pen. And then with this power constraint, we're going to get this nice thing here. In fact, we can show that the simple case, obviously, when we just do regular TDMA, we're going to get this. And even in the low signal to noise ratio case, when we get this guy, you can show that this green region is always going to be covering treating the other guy's noise. So in other words, the green region is always going to be bigger than both the TDMA case and both the as noise case. So this time division multiple access with power adjustment is superior to both of them.
So remind me, like the normal TDMA, you have just no power constraint or equal power for each of the
normal TDMA is basically just saying don't change the power for the block. So in other words, we're not dividing, we're not increasing the power of the bits of the code word that we're sending at alpha fraction of the block, by 1 over alpha. So I think if we go back to this page, you'll see the difference. I didn't really, like I said, I didn't think properly about the figure versus these things. I have to switch back and forth a lot. But here's the normal one, the normal TDMA. Notice that I'm not adjusting the power at all. And here's the power control guy. So it's a crazy difference with this guy versus this guy. So we're still doing a mixture, right? But now it's not a linear mixture. It's not just a linear combination of these two extreme points, because the C function is not a linear function. C is a concave function, so you get this better bound. Now it's still an inner bound. It's still an inner bound of the true polytope. It's also FDMA, frequency division multiple access, where we just basically split, we do filtering and we split the bandwidths of the resulting senders, and you share the same channel at different bandwidths. That's pretty straightforward. Successive cancellation and subtraction. This is, as you will see, is one of the best cases. So this is basically we receive y, which we know to be basically this combination of the code word for x, the code word for x1, the code word for x2, and z. And we start out by decoding W2 and we treat the code word for W1 as noise. And so that basically gives us this point. Right? So when we treat W1 as noise, we can communicate at a rate up to this, right? Up to this bit here. Now once we've got W2, then we can subtract that off, and we form a new received word, which basically corresponds to a code word that has been, presumably, if we've got the right code word for W2, in which typical set theory guarantees we will get if we have long enough block length. We've got a noisy version of the code word just for W1, and we can decode that message at this rate. Because now, in some sense, we've removed the effect of W2's code word, because we've coded for it. So here's a block version of this. So basically, we take Y, we send it into a W2 decoder, we got an estimate of the message for W2, we re-encode W2 to get an estimate of W2's code word, we subtract that off from Y, and then we have to send it to a W1 decoder to get W1, and then the resulting messages are W2 hat and W1 hat. So what this means from this decoding strategy is that we can get either of these extreme points. We can get either this point or this point. And then we can get anywhere in between using TDMA. So that then is then, so on this figure basically we can get, let's go to this other figure. This basically means we can do better than, oops, where are we? We can get either this point here, or this point here, or anywhere in between. So we can do better than the TDMA with power control. It's successive decoding. And so here are the figures. So basically this means that in the Gaussian case, the achievable region is in fact a polytope. Because we're just basically the only thing that we're really changing are the power constraints. Not really, the distribution families are not really. I mean, in the discrete case, you can get very, very different discrete distributions. Here, everything's always a Gaussian, and the only thing that's controlling it is the power, is the variances of these Gaussians, which are the corresponds to the powers. Okay. So, any question about this?
So, what's the resolution for the FTMA case? Is it like TDMA?
Sorry, say again?
The resolution for the FTMA case.
So it says down at the bottom. So basically, the TDMA with power control can get this green region, and the FDMA can get this as well. But the successive cancellation subtraction can get the entire region. So the FDMA can get the same thing as the green thing. Okay, any questions? Is that 20 after? I don't believe it. What happened to the last 10 minutes? I thought we had 10 more minutes. Okay, so I'm really going through a time warp. So I apologize about the video breaking. I'll debug it. I'm not sure I'm going to get it working by Wednesday, but maybe we'll try again on Wednesday. But I think it's honestly it's a problem with my laptop. I think it's crashing. So I'll see you on Wednesday. Wednesday's going to be our last class. I guess we've got a lot of stuff to do on Wednesday, so I might go a little bit faster than normal on Wednesday because I really want to get through Slipping Wolf and the broadcast channel. And if you guys really want, if you'd like to have a class on network information theory, a third quarter of IT and some coding, lobby the departments and say, we need a class on network information theory, because obviously we're just touching the tip of the iceberg on network information theory at the end of this class. I think in other universities they have a third quarter of information theory, which is just network IT.
We need that to network information theory is pretty much that's classical right now, right? Lots of stuff. So
yep.
The course by itself.
Yep. So lobby the E department. Send mail saying, we love this class, we need more IT. Okay, I'll talk to you guys soon.